welcome. It's great to have you here. Thanks for joining us in this presentation, kind of interview discussion. The idea is for Samuel, who has recently completed with flying colors the Python programming course, as well as the data science and machine learning course, and has been digging into deep learning and Flask and a bunch of other stuff. And he did a great job on his capstone report for the data science and machine learning course, and we thought it was so great. We asked if he'd be interested in presenting it to the community as a good example of of what you can do when you get through these programs, as well as something to kind of shoot for. So first of all, thank you, Samuel, for joining us.
Yeah, totally.
And
glad to be here.
Yeah, and so maybe just to give a little context before we dig into the presentation, what got you into data science and machine learning?
Yeah, well, so I was kind of spending a lot of time sending out short stories and poetry that I wrote, getting published through different presses and stuff. And while doing so, I was looking online at some like writing jobs, editing, and mostly editing and like tutoring and English teaching, stuff like that. And while I was on there, I kept seeing data science and data analysis, and I was like, what is that? That's such a vague, data. What is data? It's like, so then I don't come from a very tech background, even though I've been, on computers my whole life. My experience with AI was mostly just algorithms in a video game, like Civilization or Age of Empires or StarCraft. And anyways, so when I saw data science, data analysis, I was like, I don't know what this is, but it seems popular, and I do like data. I like statistics. So I looked into it, and the more I researched it, the more I realized this was like the thing I had been looking for. I'm one who really likes patterns, and I like seeing patterns. It's different scales, and I love how the more you zoom out, the more you see patterns from things. And I think that curiosity for patterns and for the way that things relate to each other, like interrelation, is fascinating to me. So I looked more into it and realized that it was a lot of fun. I was pretty intimidated at first by the coding stuff, because I didn't know how to code. And I didn't know if I wanted to end up doing web development more or data science more. As I got into it, I just started really finding a groove with machine learning and stuff.
Nice. And so would you say now, do you have that same, you said it was intimidating when you got started. Do you have that same kind of, what's your feeling now when you look at new code, new projects, new technologies, et cetera?
Yeah. Well, I think for one, this, I don't know if this is for everyone, but one of my like strategies when I look at like really code that's way more advanced in some ways than what I'm familiar with yet, I tend to just be like, okay, glaze that over for now, keep reading the main points. It's like when I've looked at a book I'm reading, like for a class or just a heavy book, I tend to just get comfortable with the fact that I'm confused. Hi. I just try to get comfortable with the fact that I'm confused and realize that that's learning. But yeah, I think what clicked for me was the language part of coding. Once I started coding, and it was only within the day probably, I realized I was writing in another form. So it just, for me, it is just language. And I love math, so I didn't realize it really snuck up on me, Ryan. Like it just like code is just this intersection with language and math that really got me interested. And I think once the language aspect connected, I was just all in.
Nice. Very cool.
So yeah, intimidating at first for sure, but then you start to notice the tricks, or the language, you get the vocab.
One of the things that, the reason I bring that up, one of the things I'm always encouraging people with is that if you just kind of put a little more, keep putting time into it, the mystery kind of unravels or reveals itself. And a lot of one thing that I love is when you get to that point where new technologies, new languages, new frameworks, new libraries and tools, they start to lose that intimidating factor, and they just become more of just what you're going to learn next, or what you're going to do next, or something that looks interesting that you might that you might be able to use in one of your projects, which is always a great realization. So speaking of projects, what did you so what you're going to show us today, maybe give us a little context as to what this project is and why you chose it.
Sure. Yeah. For those of you who haven't explored it yet, the data science and machine learning course has an awesome capstone at the end of it to get your portfolio going. That's actually one of the main reasons I really liked the portfolio project and program in this school. That one of the main reasons that helped me choose CodingNomads. But anyways, the prompt is just to kind of find something that you care about, find a problem that needs to be solved, because ultimately data science is a problem-solving field, and also a problem-finding field. Sometimes it's like, we need to find the problem here before we can even solve it. And so I think for me, how I came to the solar energy thing was I was really fascinated by different technologies that could mitigate climate change risks and damage. And I want to do something that I can wake up in the morning and look forward to and care about, and go to sleep that day knowing that I did something worthwhile with my time, according to my own interests and stuff.
Right.
And I was going through a lot of different options. One of them was a fake news detector, because I'm fascinated by NLP, as you might imagine with the writing thing. But I kind of was like, well, I want to do something a little more substantial. There's a lot of fake news detectors out there. And I was looking into a construction estimator, how to look at a project and web scrape a bunch of lumber prices and stuff, and get estimates on. And because we're remodeling a house in the backyard at my place with some friends, and then I realized I don't know how to web scrape very well yet, and I got to do this data science project. So I was like, oh, you know what? One of the key aspects was I was wondering about solar energy installment, and I wanted to know how well you could estimate the potential for a given area for solar output. And I remembered a friend of mine who's a data scientist in Texas. He was telling me about a friend of his that invented this GIS tool that estimates solar output. And I was like, I want to do something like that, but I had to kind of tailor it to where I was at. And I realized that there's a lot of free data online, and a lot of people have done things somewhat similar or whatever, but there's a lot of room to play with it. And I found this great data set. I found a few papers that worked with it. And then I also found that there was some stuff that I kind of wanted to focus on more that the other papers hadn't focused on yet. So I kind of collected their stuff and then went for it. Does that get to the question?
Yeah, it does. And I think it kind of leads us very well into kind of starting to look at your project.
Sure. Yeah.
Let's take a look at what you did here. And I think one of the interesting things, what I like about this capstone project is with a lot of what we do is coding, right? And we build software applications. But when it comes to data science and machine learning, oftentimes what we're looking for is knowledge or a summary, right? A report of what our findings are based on all of this analysis. And I think your project here does a great example of that. So I think you should have screen sharing options.
Cool. Thank you, Ryan.
Yeah.
Let me find the right screen here, or else you'll see some text edit notes that are just a jumble. Cool. Well, thank you, everybody. By the way, I really appreciate you all coming out to this. It's super exciting to
we got a nice
work on this with y'all, present it.
Nice crowd here today.
All right. So first off here, I picked it out. I found the PDF that I uploaded to, or that I pushed to GitHub, and I just wanted to show how useful GitHub is for anybody that's new while doing this. I just went right to GitHub if I had done it on this computer or not, and then I brought it up. So also, that's to plug my GitHub if anyone wants to check it out. It's not the most exciting, but there's some cool stuff. I have a video game or a text-based game I've been writing in there. So that was my first project that really got me into coding.
Nice.
So check it out if you like. It's not done. All right. So to start off with, some people might not be familiar with machine learning necessarily. So essentially, it's just teaching, writing math equations, algorithms actually, that can take in information, estimate and predict, and then test that prediction and learn from it and adjust their formulas and able to better predict. So that's kind of like how I would sum up machine learning. So in this way, we're trying to engineer a machine learning model that can predict solar energy potential according to a region rather than just through what's the main factor usually, which is DNI, direct normal irradiance. And without going too much into that metric, that's kind of a tricky metric to use because it can be very finicky and it can change according to like a microclimate. So it's really hard to really predict an overall amount of solar that you can get out of a region. So some people have figured out how to use kind of a roundabout way to estimate that, which is to use meteorological data and location data, and using that as a proxy for measuring the amount of sunlight that hits a certain area. A few people that have told about this have been like, what did you come up with, like Arizona? And I was like, yeah, pretty much. So like it's always good to be in the real world, I think, with data, because it can get so off the ground, kind of like abstract sometimes. And I think those questions or those remarks are pretty good, because I'm like, oh yeah, why am I doing this?
Mm-hmm.
And for me, it has a lot to do with like the growth in demand for electricity. That's we're going to be seeing more and more of. It's projected to grow by 30% by 2035, but we don't have enough solar infrastructure to support that growth without and not use carbon-based fuels. So the issue for me was really important, but again, yeah, where do you put it besides picking Nevada or Arizona? And the thing is that certain areas can show can actually provide a lot more solar energy depending on the side of the mountain it's on. And as we'll see, it also has a lot to do with the moisture in the air, ambient temp, and air pressure, altitude, all kinds of things. So we're going to go into some of those.
One quick thing I was just thinking is that having something like Arizona, which is totally accurate, right? It's a very real world, like obvious solution to where solar is probably going to be good. But having that kind of base knowledge or kind of obvious truth in your data, then you can say, okay, where else that might be unexpected performs like Arizona does, right?
Yeah.
Maybe there's Southeast Ohio has the same or better, solar gain or irradiance than Arizona does, so it can give you like a nice beacon of truth in a way.
Yeah, that's a really good point, Ryan, because it does give you a benchmark, and benchmarks are the magic sauce for us in data science. It really helps. I've been doing some NLP projects with summarization, and there's it's not like there's a ton of summarization, there's not a ton of data that I've found that gives you a very solid metric. I mean, there's been brilliant ways of getting around that through different NLP metrics that I've been working with. But yeah, I was, doing this current project I'm on, I was like, oh man, I really miss having just some numbers, to put into a regression model. But yeah, so I mean, and also to bring up the location thing, I think another important part of this is that sure, yeah, Arizona could be a complete solar field, right, or whatever. Actually, that would suck because there's a lot of beautiful places in Arizona, of course. Yeah. But Yeah, no, if say we did cover it in solar energy panels, like the thing is that transferring electricity actually loses electricity, which is
Hmm.
something I didn't know until I engaged in some domain research into this field, which yeah, really taught me a lot about solar, and just electricity in general. But yeah, the thing is that we have to find ways to locate power collection to a more local area,
Hmm.
because the transportation and distribution of electricity can, and we'll get into this. This is more into the conclusion in the paper, but that can actually lead to at sometimes 30% loss of electricity. I mean,
Hmm.
in Idaho, for instance, it's like I think 9 or 10% average loss every year of electricity gathered, and that's a lot of fossil fuel electricity that's just going to waste.
Hmm.
So yeah, we can't just rely on sunny places. We need to find the exact spot, right,
Right.
in an area, or at least, I mean, nothing's that exact with regression. We have to minimize our error. So anyways, yeah, that's kind of like the motivation for this, beyond just like, picking a sunny spot. But anyways, I'll get into a little bit of the data actually, because I realize I've been kind of skirting by that one. So this is a notebook, Jupyter Notebook. For those who aren't familiar, it's a really nice software for coding, especially for data and machine learning. So there's some contents there. So this is an import thing. If you're not familiar with imports yet, don't let it scare you. It's just how you bring in a bunch of different tools. You like want to create an environment, and you're like, oh, there's all these open source coding tools that people have written. I'd like to bring them all in. So you bring them all in here, and we got one for numbers that does all your number calculations. This one's for data frames and data sets. This is the just to be safe, I imported it twice, and then
Pandas too, it
imported that
looks like.
twice.
Yeah,
Yeah,
it
yeah.
looks
That's the curse of copy paste, I
uh-huh.
suppose.
Yeah.
So yeah, just it's good to measure twice.
Yeah.
So then we have some different algorithms here that I've imported, all from scikit-learn there, and some more here. And
And
then
scikit-learn is an open source library, pardon my interruption,
oh
for
yeah,
for all kinds of general machine learning style tasks, right?
yeah, super cool. Even if you're not familiar with data science stuff yet, or you're maybe earlier in your coding journey, I'd really recommend checking out scikit-learn, because they're one of the best. They have one of the best educational frameworks for me that I've seen. Everything is just written out, and it's all linked well. Like, with Python, I can always look at the Python documentation, but I have to search through stuff. And I do. It's just that the scikit-learn, while you're typing it in, you can have these pop-ups that show up in Windows that you can go to that give you examples and explanations. So really cool. So I really relied on scikit-learn on this. And then this I spelt that wrong, but here we have the neural network that I tried out. This is if anyone's heard of deep learning, this is a deep learning algorithm. This is a very basic one. They've gotten a lot more advanced, as I've been finding out more lately, as I've been learning more about deep learning. But it was really fun to try that out. So yeah, anyways, whenever you get a data set, and the best thing to do is just start searching around and playing with the data. I
One
think.
quick question on the data.
Sure.
Where did you find the data, and what format was it in? Was it a REST API? Was it a CSV file? Is it something you
Oh yeah.
downloaded? Yeah, it looks like that's it right there in the red text. CSV
Yeah.
equal. Yeah, okay. So it was a
Yeah.
CSV file. Where did you find that CSV file?
So I was looking on Kaggle,
Mhm.
and then I found actually, you know what? I was looking on Kaggle, and I didn't. I found a few data sets. This one I found on Medium, actually, because I was looking up solar energy projects, and this person had done a walkthrough of how they worked with this data set, and then and it's linked in the paper.
Mhm.
But yeah, anyways, I found that article, read through it, and then I found the data set that they attached to. and worked with, and I went into that. I also read into Passon et al. This represents a paper that worked with this from a more academic standpoint, and it's a super great paper if y'all want to read a good science paper. And yeah, they spell out a lot of the details of the data set in there. But it was all free. It's on a CSV. So yeah, what I did code wise was I save it to this variable here and read it in. You can just create a data frame out of it. And a CSV file is comma separated as the CS. And it's just like text with commas, and it's organized in a way that you can read into a data frame really easily. It's a good way to share data across systems and at large amounts.
Right.
Yeah, so looking into the data, we've got like a few different things here to show you kind of just like a summary. EDA here is exploratory data analysis. So it's just like looking at the data, exploring it, analyzing things, whatever you find. And this is, I think, one of the funnest parts of the whole thing, because you step into it and you're like, whoa, what's going on here? Because a lot of these data sets are so high dimension, you can't picture the data, where I can't. So yeah, we've got various variables here. We've got location, date, time, as you can see, all these different. This here is our target variable. So we're actually solving for that one.
Okay.
What were you gonna say?
And these are essentially like the headers of the CSV file, like the what data is in the CSV file, the column names, essentially.
Yeah, those are all column names, and so you can see it in this format here. It kind of gives you a little better of a view.
In this format that we're seeing, this is just the output for when you run in a Jupyter notebook. When you right now you're using pandas, it's a data frame. So you say df.describe, and when you run that command, you get that output, right?
Yeah, and they format all of this. It's really great. Like this is all your summary statistics. Sorry, is there a noise coming in from that mower next door?
I do hear a little bit of a mower, but it's not offensive.
Okay, cool. Sorry about that, y'all. So we have a df's the variable for the data frame, as you see. And then this is the info. So this just gives us a very basic breakdown. We see that there's no null values in any of the rows, which is great. And then this gives you the data types. Floats and ints are numbers. Some of them are objects. We'll get into that. But then, yeah, df describe gives you a whole breakdown of summary statistics. And so just to go through a few of these real quick, this is, right here we have the Yermadomri. But yeah, that's year, month, day, hour, minute. So that's all reflected here as well. You'll see sometimes in data sets that you have some redundancies, but they're not quite redundancies depending on what your task is. So for me, they were redundant, and I did explore the use of this one in particular, but found that I didn't really need that one as much for what I was doing. But you can see, for instance, like this is a humidity measure, and let's go back to count mean. So the mean humidity, for instance, would be like right here, right? So we have the mean humidity, and that tells us kind of like a benchmark, right? Like we were talking about earlier. That's, if it's higher than that, we know it's a little higher than average. If it's lower than that, we know it's a little lower. So these are all your averages in this second row here. And again, I want to draw attention to polypower here. This is the variable we'll be solving for. So, a basic breakdown of that is in data science and statistics, you have independent variables, which are all the ones you use to make your that you observe to use for predictions. And then you have a target variable, which is the one that you want to predict. So I'm going to be using all these different stats here to solve for polypower here. So that's kind of an idea of that.
At the risk of total redundancy, essentially what we're looking at is output from like weather stations, weather meters.
Yeah.
And is this all over the US essentially?
Yeah,
Nice.
yeah, totally. And I got a little map here for you. So
Got
these
it.
are the different sites. Now I love data visualization, and there's a slideshow I have here, which I'll draw on a little bit, but it's got a few different key visuals for you. We got, one in Hawaii, one in looks like, or one not too far from Maine in California. We got one in Baja. Yeah, various places. These are all different Air Force bases across the country, and they have the means to record all this stuff, so people were able to leverage that data. So the target value is output in watts over a period of time, so that's polypower.
Okay.
Yeah, and there's 16 features. Features are synonymous with variables, if you're familiar. If you're not familiar with the term features in this context. Yeah, and it was collected over 14 months, and there was 7 distinct climate regions. So that drew my attention right away, because we have 12 different locations. You think the more locations the better, right? But they could each be a mile away from each other. That doesn't give us a very diverse data set. So sometimes when you're looking through data, it's great to really look at how diverse and generalizable this is, because we want to be able to generalize these predictions for whatever we're building, like an API that can help you estimate solar potential, for instance. So you want to be able to do that with a region it's never seen. So anyways, I was really attracted to the fact that it had 7 different climate regions. I mean, think about the difference between like the Great Lakes, for instance, and Hawaii. So between the two of them, we can get a pretty good idea of how to estimate and how to predict, I think. Some more summary statistics. I kind of overkilled it here just because I like looking at things from different angles. But also, with this one, you can kind of see a little more condensed version. So for instance, latitude, the average latitude was 38 degrees. And you'll see that, like, for instance, and then I separated here with the target variable. And now this one was, this is just a little code I did for myself, and you might be familiar with print statements. And then here's the df describe again. But then what I did was I separated the target variable, and I really like displaying stuff in my own format. So that was kind of what I did there. And yeah, so anyways, that's some of the summary statistics, but summary statistics aren't everything. So they're just a summary. So here we go. We have a heat map, which is one of my favorite data visualizations here.
Can we real quick
out a little
just
bit. You were saying, Ryan?
I know that the code above might be a bit dense for most of us, but right there for the heat map.
Yeah.
So how did you, and we don't need to go into great detail about this, but how did you figure out these, the plot.show, the third line simple enough, but like that second line, that heat map function, where did you learn that?
So yeah, great question. So I was looking up, so SNS here is this library called Seaborn. And they have a bunch of different data science visualization tools for you, like a heat map. What I did was I was looking at different papers that used different metrics for different subjects, and I kept saying heat maps. And I just started looking through the different available tools in the Seaborn library, and found this one was really informative. I also saw it in some of the papers I was reading. So then what I did was I figured out how to make a very basic one. And then I read into the documentation of it and found that these are your different little settings for changing the way it looks by way of the color. For instance, this could be red and blue. I chose these colors here, and I chose the line width. For instance, you can change that to double that, and then these lines here will be that much wider. So every little thing in this is controlled by just this line of code, really. But yeah, for me, it was about just trying hundreds of different combinations, I think. Yeah.
And
And
then,
finding the one that best represented it.
while we're on that topic, Raz asked a great question. For the heat map, it looks like you used a Pearson correlation. Why did you decide to look for linear correlation using a correlation coefficient such as Pearson instead of a nonlinear monotonic relationship using correlation coefficients such as Spearman's rho?
Yeah, that's a great question. I think that it would have really helped if I had known that there were more options. I knew of a few different options, but one of the reasons that I chose Pearson was because I was most familiar with it, and also because I feel like it gives a very, I found that it gives a very relatable and understandable presentation to people, because the linear thing is a little bit easier to comprehend, I think, for me, myself, and I think for others. Does that get to the question?
I think so. Raz, if you've got additional thoughts or questions there, because that's a little bit outside my domain. So I'll take your word for it. But in the meantime, what are we looking at here when we see this heat map?
Yeah.
What is the white one versus the dark -1 versus, what are we looking at here?
Yeah, so the lighter it is a more positive correlation, and then the darker squares are a negative correlation. So it's easy to think of positive and negative as good, bad, and it's good, but it's better to drop that and just think of it in terms of like they move in different directions according to one another, these statistics. And so a negative correlation can be really useful when we're trying to make predictions. That's why it's good to have kind of a range, and then you find that the ones in the middle don't really yield a lot of information for us that's usable, at least. So these ones down the center of the square, diagonal, that means basically, like, if you look like humidity and humidity have a complete positive correlation to one another. So when you think of it that way, it's kind of like, well, duh, right? But then that gives you a benchmark to kind of see the other things. For instance, you got like, let's see, what's a good one? The ambient temp and polypower. Like, so here's our target variable, right? This is the one we're going to be looking at a lot, and it's reflected on both sides of this. So you'll notice that these are mirrored.
Mm-hmm.
For me, that's cool because it helps me understand it. But we have a ambient temperature and polypower have a positive correlation that's pretty significant. So essentially, that means that the higher the temperature in the area on average, or whatever, the more power we're going to get from the solar panel. And that makes a lot of intuitive sense if you think about it, right? Because like Arizona's pretty hot, and it has a lot of sun. Where there's a lot of sun, there's a lot of heat. So, there's some things when we look into this initially that are kind of more obvious than others. And then there's some things that tend to surprise you, So we'll look at some of the different things polypower correlates with. It doesn't have a correlation with pressure. Visibility, it has a little bit here. But something that stood out to me was humidity. So like humidity levels can actually negatively correlate with polypower. So if you think about it, like the higher the humidity, the lower the power you're collecting.
Mm-hmm. Okay.
Right. Which when I think of it through there, I'm starting to think, well, oh, that's interesting. I didn't, before I really researched this domain, I didn't realize that water in the air can actually really reflect a ton of sunlight and completely change our power collection. Mm-hmm. So these are some of the things I noticed. Is this heat map making sense to everybody, or anybody have a question around it?
Yeah, makes sense. Makes sense to me. It's fun to just explore, what's mm-hmm. negatively correlated, what's positively correlated.
Yeah, like cloud ceiling and humidity are mm-hmm. negatively correlated. Interesting. I mean, I'll leave this, I encourage everyone to look into this more. We don't have the time to go into every detail. but it's a lot of fun to look through them. And Seaborn, I just want to recommend Seaborn is like, go through my notebook, rip off this code, and put put your own data into it and see what happens. It's really fun if you want to. Seaborn's got a lot of really relatively easy to use tools for data visualization.
I'm going to drop while you mention that, I'm going to drop a link
Sure.
of this project into the chat here while you're chatting.
Oh, thank you, Ryan.
Yeah.
So we'll get into a little more of the nitty gritty. And that doesn't mean it's not as fun. It's actually quite fascinating if you like math, I think. And there's genius ways of taking data and maximizing its potential for you. So we'll get into some of that. Here's some pre-processing. So what we did, just to summarize, we've gone through exploratory data analysis. That's just kind of getting a look at stuff, right? High level. Then I'm going to split the data here into a training set and a test set. The basic breakdown of this is you have, for this one, you have an 80% training, or 80% of the data is reserved for training. And then the other 20% here is held out, and we don't look at that until we're ready to test the model. And that gives us like a view of data that this model that we've trained on the training data effectively hasn't seen. So this is a little pie chart thing to visualize it. And this is what it looks like in code. What I did was I dropped, just to explain this a little bit, I dropped y, which is going to be our polypower variable, the target variable. And then I dropped it here too. Basically, that's just kind of separate them. I did a train test split, which is programmed into scikit-learn, and they do it for you there. And then I dropped the old ones. And what that did was it just made two sets, training set, test set, 80-20. And then down here, I got to one hot encoding. I won't completely go into this, but this is a super fascinating invention I didn't know about until I started coding this last year. And it's the way you can take object data. Remember, up here we have locations and object variable, for instance. And you can actually take an object data, which is not a number, and it might just be a location, right? But then what this does is it gives you a matrix that says it's either this location or that or not, right? Like a binary representation. So then it makes a matrix in which you can see, like, say there's for this one, there's 12 locations. So there's going to be 12 different options. And if the data was collected at one site, it'll have a 1 under that code and a 0 if not. Essentially, this makes it so that we can start mathematically processing data that is not necessarily math data. So what I did was I did that to train and to test sets. And then I created a column index. This is just, I noticed I was really needing this throughout the whole thing. So one of the fun things about coding and stuff is there's so much stuff you can do to like play around and stuff, but there's also all kinds of ways to customize everything you're doing. And the more I did this project, the more I realized, like, oh, I don't have to wait for, I don't have to necessarily find exactly what I'm looking for on Google. I can write this stuff, and it felt really empowering to be able to actually write my own code for some of these things. And I, again, it's like I started the Python course just like, whoa, this is really hard to understand, and then by the time I was doing this data science program, literally like 4 months later, I was like, oh, wow, I could just write this code up real quick. And it's still a little difficult because things are challenging as you learn them, but I was really surprised I had already learned some of this stuff,
Nice.
Yeah, and then so this is a really important part here. So scalars, if you're not familiar, this is a way to get all the data into a similar scale. So if you've ever been in a group of people that are like all talking about different things, but they think they're talking about the same thing, and you're just like, oh, why is this argument happening? They should have been scaled into the same conversation. So all these numbers, like how are we going to compare, for instance, altitude data with humidity data. Those are different numbers, right? So what we do is we put them in a relative scale together, and then they can have a conversation with each other more effectively. And then this is a cross-validation code. What follows here is just some code I wrote. I won't go over it much, but this is a cross-validation is a huge part of data science, and it's a way to validate our findings by really using different sections of the same data and really economizing the data, maximizing its potential. Pipelines are an effective way to just kind of set your code so that you don't have to rewrite every step of it every time. So pipeline there, and I made a little function for that so I could just add to a list of pipelines because I was using various different ones. Learning curves, I wrote up a little learning curve code based on some stuff I found. And then I wanted to just add scores of the predictions to my own collection. And so I have a dictionary here. You'll see on, if Python people, you'll recognize that. And so this gives me an ability to like log everything I'm doing. And you know, this is a beginning project for me. So I found that there's a lot of other ways to do this now, but it was really fun to kind of write these myself before I understood the different options. But nowadays I'd probably find some other stuff too.
Code, when you go back and look at old code, it's kind of like going back and looking at an old journal entry or something, and you're like, oh my gosh.
If I had only known.
Yeah, if I'd only known. Yeah, it's always like that.
It's who is the idiot who wrote this? Oh, it's me.
Yeah.
yeah, totally. So yeah, I'm just looking through this, and it's fun. It's fun. And some of the stuff I'm like, wow, how did I you know, like after a little time I'm like, whoa, I forgot I did that. And I you know, it's nice to see when you go back through it. When I was going through it this week, just kind of being like, this was a lot of fun. So then after we did some of these sort of coding things and set up our functions, and remember, I organized this after the project. If this is not what your notebook looks like when you're doing a project, that's normal. My code did not look anything like this until I had gone through and edited it. So, you know, I, for instance, wrote this function towards the end of it, of the project. So when I was really doing all my predictions, and then I just moved it back up there. Anyways, some more data analysis here. One hot encoding. This is for a second heat map. And this one might be a little easier to digest. This one has some different variables here and some dropped variables. So it's a little bit more condensed. And then I took out the other side of it, so you can just see kind of a more simple one. I thought that was a nice complement to the other one. And then feature selection. So this is really where I focused my time and energy a lot in the project, because like there's been other papers that had focused on different ways to do this that got pretty great results prediction wise. But what I wanted to focus on was how to really select the right features and why. You know, I was just curious. So I looked up a bunch of ways to select features, and you know, to fill you in there, it's like the features you select and what you put into the data directly affects the quality of your predictions. So if you use the right features, you're going to have better predictions, right? Than if you use ones that, for instance, don't correlate. It's like some of these ones that have a very low correlation with polypower. I'm probably not going to want to use, you know, like this one, for instance, the date. It turns out that date doesn't really, doesn't always affect it super significantly. So anyways, you can actually cut down the amount of features you're using, and it gives your model an ability to better harness the momentum in the data. And that's, you'll learn about that if you're getting into data science. It's something regarding the cursive dimensionality. So too many dimensions can, you know, kind of convolute stuff.
It's kind of like,
so this is a learning.
Maybe just to throw in an analogy, and correct me if I'm wrong, but let's say you were doing facial recognition or something, and you're trying to compare, you know, all different kinds of pictures of people, whether or not there are trees in the background shouldn't necessarily be, it's not relevant, right? But it is in the image, and your algorithm is going to be looking at that. It's a feature. Are there trees in the background or not? And when you're trying to compare two faces, it's not one that you should be concerned with. Was that about, yeah?
Totally. It's kind of like
Okay.
when I was saying earlier, sometimes it's healthy to know what to glaze over for the time being. You know, and then if you wanted to like make one that was for take your best adventure pick for Tinder or whatever, you know, you might want to include trees in it or something like that. So it depends on your, you know, it depends on your task, I suppose, you know. Anyways, we have I'll skip through a little bit of this. The recursive feature elimination. So this algorithm goes through with it's a wrapper which uses an algorithm called extra trees regressor. Without getting too much in the details there, in the weeds, so to speak, we'll just kind of move through it. What this does is it goes through and it takes the cross validation score, which is just a metric for finding out like how well your model's doing, to sum it up bluntly. But yeah, and then it goes through and it automatically eliminates features that might not be supporting the predictions, and then tries that out, and it tries a bunch of different combinations out. So I was able to get a score here of 63%, and that's a R-squared score. It essentially explains, it's a metric which tells you how much of the variance is explained by your model. So you know, theoretically, you want more of the variance explained. So a higher percentage in R-squared is good. And what we're trying to do is reduce error, right? So then this code here gives us the feature importances and then ranks them. And these are the different scores I was able to get on going through just with that and then here's like a little breakdown. You know, this is a for loop, and you might be familiar with those if you've started your journey so far. They come in handy all the time. You'll never stop using them in my experience yet. So these kind of reflect the different things that played into, you know, what was most important for feature importance.
And so it looks like date, latitude, ambient temp were kind of the yeah. Okay, yeah.
Right. And so, which is interesting because, right, like I, for instance, just said like date doesn't really tend to correlate with this, but this algorithm found that the date can actually influence that a lot. Now, whether we're going to use that for generalizing to a model in other contexts with our model, that's another issue. Like you'll notice that location is no longer in here. I made the decision to take out location out of the data, and you'll have a lot of chances to, I guess, intuitively engage with the data, because there's a reason why it's not just machines doing this, right? You're bringing in a thing that a machine can't do, just like the machine's bringing in skills that you can't do, right? So sometimes you might want to ask yourself the question, okay, location tends to really correlate with all this this stuff that I'm looking for, but is that going to help me if I'm trying to use this in like, say we're going to France and we want to do this, you know, and look for solar potential in areas? It's not going to really help us if we know that Arizona does really well, you know, unless we're using it as a benchmark, like you said earlier, Ryan. But what I realized was like location data isn't necessarily going to generalize. So that's something that you'll get into with data science, is like really asking yourself, what am I trying to do with this? And is this really going to help me in the long run?
One additional interruption there. We are running a bit low on time. We have about 10 minutes left, and we do have a couple pending questions. So we'll have to maybe let's kind of zoom a little bit towards the outcome, and then we can open it up for a few questions as well.
Yeah.
Not to fly by all these really cool visuals.
Yeah, no, I totally agree. I was like trying to figure out how to get through this. But yeah, I'll just scroll through for your viewing pleasure. If you like graphs like me, you know, there you go. You're welcome. This one, this one was a real surprise for me. You know, there's a lot that, depending on the angle you view the data from, it'll really be confusing sometimes. Like, I could go into this one, but yeah, this is a k-fold validation that I ran. You know, this code was partly made, but a lot of it I collected. It's kind of Frankenstein code I collected over the internet, and there's some citations in the paper. But yeah, and then we got the initial model. So this is just a base model called a dummy model, dummy regressor. So I should have said this earlier, but this is a regression problem rather than a classification. So it's not like yes or no. It's like, where between yes and no are we on a scale, you know? Okay. And so, or maybe yes and no aren't even really significant in that context. But so anyways, we have a dummy regressor, which kind of just gives us a base. Like if we had a very basic model, what score would it find? And what that does is it gives us that benchmark to see like, okay, so the scores for the dummy model, this is again from my scoring code that I wrote earlier, that logs all this. So like the scores for the dummy model, it had a mean absolute error. This is root mean squared error, R squared, and explained variance. These are pretty much the same in most contexts. Anyways, with these metrics here, you want a lower score, and with these ones, you want a higher score. But anyways, this gives us like a ground level idea of what a regression model should be learning at least. So this isn't meant to be a good predictive model, but it's meant to give us context. So we'll see that as we build other models, we'll increase our scores. So the dummy there, I found these joint plots. I actually did a little more graphing than I maybe needed, just for fun. I really encourage you all checking out Seaborn's joint plots. They're super fun. So one of the main ones, this is the one that yielded the best results, the random forest linear regression here, the random forest model. And here's the pipeline. So basically I could just add in, I make the pipeline here, and then I just put add pipe, and then it puts it into that dictionary I made earlier, so that at any point I can just bring it right back up. And I can also bring it up after, you know, I've messed with it. I can bring up the default version, which is really handy. So as training examples accumulated, their training score got better, and then our cross-validation score also got better. So we see an improvement steadily going forward, which is good. And in R squared, that one gives a nice visual. So this was something I found out while doing this. This is a hyperparameter tuner. So this one just goes with your algorithm, and you can set up a range of parameters, and it finds the one that best works with what you're trying to do. And this was its result. So when I tried that one out, I was able to get some pretty promising scores. Let's go through a little bit of k-fold scores. Oh, I really like these ones too. And then here we have the test scores for the random forest, and stored them there. And let's see here. So compared to 6700 for the dummy regressor, we have 2, 4, and then 0.7 right there. So a huge increase, and this represents the amount of the variance that's explained. So you'll notice it's bit mirrored because this line found the best way to get through the bulk of the data. But this is noise here. We see some outliers here that it wasn't necessarily able to account for. And that's part of the issue with linear regression models, as opposed to like a deep learning model. You can, well, we'll get into that later, I guess. So there's a residual plot. This relates to that R square scored. Another visual to look at that with. And then we have the stochastic gradient descent. So if you're familiar with gradient descent, stochastic just means random. It finds it performs calculus, multivariable calculus for you, and harnesses randomness to really get a good diverse idea of what the data is doing. I put that through the hyperparameter tuner, and I added it to it, and this is what came out. And this is the testing. So again, these are all training scores here, and these are test scores. So once I trained it, I tested it, and that's when the rubber hits the road. So this is doing pretty well in some ways, still better than the dummy, but when we compare it to random forest, not quite. We got like a 0.49 score on the R2 as opposed to 0.699. So yeah, but it's always good to try a little bit more than you think you should, I think, just to get a good view of things. Here we're getting into the neural network. So this is the multi-layer perceptron. And this uses a nonlinear approach. And you'll notice here that as you get more examples, it's still learning. So we reached the limit of training examples, yet we're still learning stuff. So in the paper, I talk about how if with more data, the MLP model would probably exceed the scores of the random forest regressor. But as of now, it's just pretty close, you know, a very heavy metal score here. So we got the R squared score, and it's just a little bit below in the random forest regressor, but like I said, and it looks pretty similar here. I think as it would have gone on though, we could have gotten way better scores with the MLP over time. And here's a breakdown of the scores. And then, you know, scores data frame, I wrote that as well right here. So yeah, there's a lot of different things you can do with all these. And like I said, I'm a musician and writer, and I didn't do this until about 6 months ago, and I was able to learn a ton about data science and coding. Oh, this is my favorite one, the KDE plot. Anyways, yeah, I could go on about graphs for days, but yeah, I was really pleased to be able to get all this under my belt in only a few months, and I feel like I really discovered something amazing.
I mean, you just kind of went over a ton of stuff, and I appreciate it. And so it's kind of like, I know that you could do, as you said, you could talk about this for a long time, because it is really interesting. You know, you got this very interesting data set, and now all of these incredibly interesting tools to analyze and explore and understand and predict that data set. And so, you know, I really appreciate you kind of zooming through that for us. We're technically at time, and so with that being recognized, I want to. No, it's you did a great job. Thank you. I want to. There was a couple questions. The one that Shadas asked, which is, which subject was counterintuitive during your studies, if there has been any?
Which subject in general? In the data
yeah, in your studies, which subject was counterintuitive, if any?
Yeah, I'd say that for a while, and I'm trying to be optimistic, but for a while, deep learning and just neural networks. I mean, in the data science program, we touched on them a little bit, and I'd say that going into a little bit of the deep learning stuff, I was like, what? You know, it's a very black box kind of setup. And then as I've looked into it, I've been able to, digest how it works a lot more. But I think that was one of them. In terms of the class material, I was like at first really having a hard time with the linear algebra. I never took calculus or linear algebra in school. And I was like, it just was blowing my mind. I mean, I love math, so it was fun, but it wasn't intuitive at first, and it came with practice.
Yeah, nice. Karel asks, he linked to a solar panel temperature. Did you also do any calculations that, well, have you also calculated that to warm also harms production of solar panels? So I think that's actual solar panel temperature. Was there any of that data that you had in the data set?
Oh, I mean, if you thank you for that. I recommend going to the paper and check out some of it. It doesn't specifically talk about the panel temperature that much, but it does talk about the ways that certain areas can affect the solar panels differently, and that'll actually affect the power output a lot. And one of the thing is that if you put them in direct sun, the heat from the sun can actually affect its ability to transfer and distribute power, collect power. And so, yeah, I found that really fascinating. I especially found fascinating the way that power lines, as they heat, they drop, and it actually decreases the efficiency of their transportation. That's one of the reasons why it's good to localize power distribution.
Mm-hmm. Nice. Well, and one thing, I know we didn't really get to look at it, but in your GitHub repository, which I've shared, you made a really nice, essentially PDF report with your findings. And so
Yeah.
for anybody who's interested in this, I definitely recommend going to check out that GitHub repository. Just, the notebook, like you mentioned, one of the great things about all of this is all of you who are watching this can go clone that notebook, set it up and and you can run it on your own machine. You can start tweaking the graphs. You can start tweaking the data set. You can start exploring with it on your own. You don't necessarily need to start from absolute scratch, to do this. You can take some interesting work that somebody else has done and start playing with it and extending it. So I definitely recommend, as you mentioned, and thank you for being so kind of, open with your project, Samuel. I definitely recommend others to do the same. And, I would like to thank you again for taking the time and congratulate you on a job well done and on, the incredible progress that you've made over the last, 6 months. It's just been phenomenal to watch you progress, and you've clearly put in the time and effort, and it shows. So nice work and congratulations. Yeah. And John, I'll let you close it out. In the meantime, if there's any other questions that people have for Samuel or for anybody else, feel free to raise your hand or type them in the chat box. And otherwise, I will stop talking and thank you all again. And I'll pass it over to you, John.
Thanks, Ryan.
Right. Yeah, thank you, Ryan. Thank you, Samuel. A great presentation. I know I felt like I was drinking from the fire hose here. There's a lot of the stuff that's brand new to me, and every time I go into one of these things, I come out learning just a little bit more. And so I should probably go through the data science machine learning course myself, just so I can keep up with you guys.
Yeah.
So I want to thank everybody for coming. We had about at the max about 30 people here, which was great. Right now we're looking for our next Tech Talk in 2 weeks, but we do have some after that. We've got a couple of folks who are set up. If you have something that you want us to talk about, something you want to learn about, drop me a line either on the forum or on Slack. Drop Ryan a line on the forum or on Slack, and we'll do our best to make sure that we've got somebody here to talk about it and to give you the type of learning, type of knowledge you want to get. So until then, I'm going to wish everybody a happy weekend. Have a good day. Thank you, Ryan. Thank you again, Samuel. And we will talk to you guys in a couple weeks.
Thanks, everybody.
Yep. Thank you, everybody. Thank you, Samuel. Great job. And we will see you all soon.
Hey, everyone. Thanks for watching. If you enjoyed this video, please let us know by liking and subscribing. If there's another topic that you'd like to learn more about, leave us a comment. We would love to hear from you. And if you want to become a coding pro, visit our website at codingnomads.co. See you next time.